What's going on, everyone? It's the EV Engineer, and in this video I have a pretty cool demo where I'm going to be writing a TCP client for the ESP32 microcontroller using the ESP IDF. So I'm going to be coding this program completely in C code, and we're going to do some interesting things such as connect to Google, and we'll write some GET requests in C using bare bones TCP sockets. The first thing we're going to do here is create our ESP IDF project. And the way we do that is we type idf.py create project, and we'll call this TCP Client. Once this is created, we can see that it has generated a folder for us. So we can cd into here, and there's some more goodies in here. We have the CMake lists.txt, that's for our build system. And we have the main folder, which has the main source file and another CMake lists.txt. So let's go ahead and let's start programming our TCP client in C. So I like to open up another shell in Bash so that I can use Linux commands because I'm on a Windows system and this is my Windows subsystem for Linux Ubuntu machine. So I'm going to cd into our newly created folder, cd into main, and I'm going to be editing this file in NeoVim. So I'm just going to start from a bare empty file for now. And I'm going to import some headers that we're going to need for this demo. And these headers are specifically for the ESP IDF framework. This one in particular is important. The protocol example is common. This is what allows us to connect to Wi-Fi. And we're going to add some other headers later specifically for sockets, but for now I just want to set up our microcontroller to be able to connect to Wi-Fi. So we're now going to need our main function, which in the ESP IDF framework is called app_main because it's not actually the real main, it's just what FreeRTOS hooks onto. So it's called app_main and it needs to be called that. And we have some checks here. These are straight from the framework, not super relevant for sockets, but if you're interested in knowing more about it, feel free to go read the documentation. But we're just checking the flash, we're checking the network interfaces, we're doing some event loop. I don't really even know what this does, to be honest. It's straight from the framework. But the important one is ESP error check, example connect. So this function call will verify that our Wi-Fi connection is good, which is going to be a prerequisite for writing any sockets or doing any HTTP requests. So let's leave this file for now, and we can go back to command prompt. Let's go back to the main folder, and we're just going to do a little test run here. We're going to do idf.py build. Now this will take a few minutes, so while this is running, let's go back and make some more edits that we're going to need. So I mentioned earlier that we're going to need Wi-Fi. So the way we do that in this framework is we're going to need to edit the CMake lists.txt. So the CMake lists.txt, well, actually there's two of them, and I think I opened the wrong one. We don't need to edit this one. We need to edit the one in the top level folder. So we'll do nvim CMake lists.txt. And this is the CMake script for our entire project. And if you recall, I mentioned we were going to need that one protocol examples. Well, we're going to need the header file specifically and all the corresponding library source files. So the way we include that in the project, or the way we tell CMake to build that component for us to use, is we add this one line, which is called set extra component stir. We give the framework path, examples, common components, protocol examples, common. So this is a ESP IDF project, just like the one we're making right now, but it has tons of common utilities for all sorts of communication protocols, such as Wi-Fi. So let's save this file. And let's go back to our command shell. And it looks like there was an issue. Yeah, so as you can see, it couldn't find the protocol examples common. That's because we just told it right now where it is, so it didn't have time to actually make it. Before I kick off another build, though, I'm going to input the Wi-Fi parameters for our project that we're going to need. So the way we do that is idf.py menu config. And this is going to open up a little GUI for us. And now the GUI has popped up. Now you can see here, there is one entry called example connection configuration. And in here we have the Wi-Fi network and we have the Wi-Fi password. Now I'm going to input these right now. The way you do that is you click enter and then you type in blah, blah, blah for your credentials. Obviously I'm not going to show mine right now. So I'll see you after you enter yours. Now, after you enter your credentials, it's going to save whatever you wrote into this STK config file. So let's just build one more time, and we should expect everything to work because we now have the path set up for the project protocols common, and we just input our Wi-Fi credentials. Great, so it looks like the part that we expected to compile actually worked. The only thing it's failing on now is it's saying, I don't know what this TCP client function call is, and that's because we haven't written it yet. So let's go back here, and let's go into main, and we will nvim our TCP main file. And just before I hit enter here, I just wanted to point out that you can see this SDK config file. These weren't here before. Until we ran the IDF Menuconfig, and then it created all the parameters for our project, and it stores them in here. So if you're ever curious what all the parameters for your project is, you can open up this file and it'll have all the configurations. So now let's click enter, and you can see here we have the function called to TCP client. We haven't implemented it yet. So let's do that. Void TCP client. And we will give this a void parameter and open bracket, close bracket. Cool. So to start, what we're going to do is actually create a infinite loop because we don't really want this TCP client to be exiting. We just want it to keep on sending TCP requests. So I will open up an infinite loop for that. And the first thing we're going to do now is we're going to create our socket. So I will paste this code in here. So what this is doing is it's creating an IPv4, so IP protocol version 4, TCP socket file descriptor. So a socket file descriptor is not a real file, but it's treated as a file. So when you create a socket file descriptor, the operating system allows you to bind your program to this endpoint. So from the perspective of your program, a socket file descriptor is a file. From the perspective of the operating system, the socket file descriptor is just the hook that your program uses to ask the operating system for various TCP functionality. So that was a very crude explanation, but that's pretty much all you need to know. We need to create something called a socket file descriptor. So before we continue, let's actually include all the headers that we're going to need to use various socket functionality. So I have these written out here, and I will just paste them right here. So stdio, obviously for printf, syssocket.h, this is really the main header file that has all the socket functions. We have a few other helper libraries such as netdb. This is for closing sockets, and then, yeah, these are just standard utilities. So we have our socket file descriptor. Now what we need to do is we're going to set up the host parameters. Now, in our case, the host is actually just going to be everyone's favorite website, google.com, because it is a very simple demo to set up. So google.com, we're going to use this struct host entity, get host by name, and that's from the library that we included above. We'll do a quick check for if host is null. If it is no good, we'll return. And let's continue. So the next thing we're going to do is we're actually going to set up the socket parameters for the host. So this here isn't exactly a socket parameter yet. It's just this random entity that we've named host entity called google.com. What we need now is something called a socket address in data structure. So the socket address data structure is all the information needed to set up the TCP socket with the server. So what information do we need? Well, we need to tell it which version of the internet protocol we're going to be using. So if you want to use IPv4, what you do is you input AF_INET here for the SIN family. And for the SIN port, we're going to be using port 80 because that is the default HTTP port. And this weird function here is called host to network. S, I'm not sure what the S is, but what this is doing is it's just making sure that the endianness of this integer is correct, because network endianness is actually big endian. So if the host system uses little endian, it has to swap around the bytes. So now, finally, what we do is we input the IP address, which is in this struct parameter. And because we used this library function up here called host entity, we have a bit of a cryptic syntax here, but we have to cast the host address as an in address pointer and then dereference it. It's a little cryptic, but it is pretty standard and it's well documented. So now we have the data structure needed for our TCP connection. We also have the socket, which is the endpoint that our program uses. So what we need to do is we have to connect the socket address parameters with the socket. And then once that is done, we can finally use the TCP protocol. So the way we do that is through this function called drumroll connect. So I wrote a little comment here: attempt to establish a connection with the server. Block until the connection is established or an error occurs. If successful, open the client file descriptor for reading and writing. So what this is telling us is that this function is blocking. So we're just going to wait here until a timeout occurs and we've either connected to the Google server or there was an issue, and we're going to be returning and printing an error message. So yeah, there's a bit of a nuance here, and I forgot to create this type name, which I will do right now. So there's something called a struct sock address. So I just wanted to make a quick interlude here if you wanted some more information on what the type def was for the sock address structure. So I have a textbook here, which is mainly what I use to learn about sockets. And you can see they have the data structure for sockets, which we use to define the family, the port, the address, and this is just a bunch of padding, so just zeros. And then the generic socket address structure. Now, they mention down here in this paragraph, the connect, bind, and accept functions require a pointer to protocol-specific socket address structures, but the problem at the time is that the sockets interface required the generic socket address structure, but there weren't any void pointers in the C language at the time. So what they needed to do is cast all of the protocol-specific socket address structures to the generic socket address structures. So that is why in my program, I also did this, and this seems to be now the official way to do it. So we need to create this type def up here, and we're going to be using this, for example, in the connect function, where we have to cast our address, or the address of our address, as a socket address pointer, and we'll be giving that to the connect function. And like I said, it's going to be connecting the parameters with the socket. So if we get past this point, the assumption is that we've connected to the server. So I'm going to be printing a little message here if you happen to be looking at the console log. Cool, so we know at this point that we have successfully connected. Now what are we going to do? We're going to be shooting off some strings to the Google server, and it just so happens that the string we're going to be shooting off is actually a GET request. So if you've never seen a GET request in the form of a string before, it's pretty cool. You just write GET and then root HTTP 1.1 /r \n host google.com, and then a bunch of other carriage returns and new lines. So, and we should note that there's no payload in this GET request. We're just connecting to the endpoint. So now what we can do is we have everything set up to finally send our TCP message, which happens to be an HTTP string, but the HTTP part isn't actually important. What you should be focusing on is the TCP part. We're sending a TCP string, and then what the server decides to do with that string could be any sort of higher level protocol. In our case, it's HTTP. So let's send our socket string. The way you send a TCP string is you use the send function, which is defined in the socket library. You give it the file descriptor, the message, the length of the message, and this 0 here is for any optional flags that you want to include. We don't want to include any, so we're going to use a 0. So now after we've sent our string to the server, we're going to want to check if the server responds. So let's create a character buffer, and let's ask the socket API if anything has been returned. So the buffer is here, and the way we receive stuff is with the receive socket function. We give it the socket file descriptor, the buffer, and the buffer size, and more optional flags. We're going to log the response from the server using the ESP log function, and I'm going to be using the FreeRTOS task delay to wait 3 seconds before we repeat this entire process from scratch. I just realized up here, so I didn't explain, IP protocol describes the lower level protocol that you want the TCP socket to use. Usually people just set this to 0. That's just the default, so we're going to be adding that up here. We'll come here, we'll add this. We're also going to be including the tag, which is just used for the ESP IDF logging functionality. The other thing we should note is that when we are creating the socket file descriptor, this sock stream here is what you use to specify that you want a TCP socket rather than a UDP socket, because those types of sockets are treated differently. So we're going to do one more thing, which is actually to properly close the socket, because if you keep a socket open and the program ends, this is more of an issue on a Linux machine or like or any desktop machine really, is if the program ends but it doesn't properly close the socket, it could have issues reopening that socket. So you always want to make sure that you're doing the appropriate housekeeping required. So the way we're going to close our socket is we're going to check that it exists first and everything's fine, and then we're going to be shutting down the socket and closing it. So these two functions here are what you need to do to shut down and then close the socket. And let's get rid of this extra bracket. So what our program is going to do is it's going to send one message, close the socket, and then it'll come back up and it'll repeat the whole process. So let's save our file. Let's go back to the command line and let's build. So it looks like our program built without a hitch. So now what we're going to do is we're going to type in idf.py-pcom3, which is the port that I'm using, flash, and then I want to monitor. And I have my ESP32 right next to me here. We're going to type in, well, we're just going to press enter. It's going to flash our device. We're going to hold down the boot button. So our program is now flashing on the device, and it is now booting up, and it is setting up the Wi-Fi connection through this example connect function. And we've now started into our program. As you can see here, it looks like we've successfully gotten a response from the Google server. So we connected the TCP sockets, and we got HTTP 200 OK from the Google server. And at the end of our loop, if you recall, we shut down the socket and we restarted the entire TCP client. And we wait 3 seconds with the FreeRTOS vtask delay, and we start from scratch. So every 3 seconds, we're setting up a new TCP client and sending a new HTTP request, and getting a new response. So everything looks like it's working as expected. So I hope you enjoyed the video. We did a pretty interesting demo today. One might call this an IoT project because we are using a microcontroller to connect a TCP socket to Google. And this is really the foundation of how the internet works. And nowadays you're able to do this kind of code, which used to only exist for these mainframe Linux computers on a small ASIC on a microcontroller. So what a time to be alive. If you enjoyed the video, please remember to drop a like and subscribe. Let me know in the comment section if you enjoyed this type of content. So for all my subscribers, thank you so much for watching. I appreciate you guys and have a nice day.